Hey, welcome. For years, the whole story of the energy transition was really about just one thing, building more. More solar panels, more wind turbines. Simple, right? Well, the story's getting a whole lot more interesting now. We're stepping into a new phase where the challenge isn't just about plugging in more renewables, it's about making sure our entire power grid can actually handle them without, falling over.
Okay, let's just park on this quote for a second, because Tim Rastl really hits the nail on the head here. This tells you that a huge, fundamental shift is happening right now. We're moving past the simple construction boom and into a much trickier, more sophisticated engineering puzzle that's literally going to change how the entire energy industry works.
And that really gets us to the heart of what we're talking about today. This big pivot from just caring about quantity to focusing on quality.
I mean, think about it. For the longest time, the only question that mattered was, how many megawatts can it produce? It was all about capacity, a race to the top. But now, grid operators are asking a totally different question. They're looking at a project and saying, okay, that's great, but how does this thing behave? Does it help or does it hurt the stability of the whole system? And pretty soon, if your project can't prove it's a good team player, it might just get left on the sidelines.
So that brings us to our next big point. Because as amazing as it is to add more and more renewables, it actually creates a brand new engineering problem. It can make our grid surprisingly fragile. Now, what's so cool about this slide is this idea of inertia. The best way to picture the old grid is like a massive, super heavy flywheel. You had all these huge, heavy generators spinning away in coal and gas plants, and their physical momentum, their weight, kept the grid's frequency incredibly stable. It was basically a giant built-in shock absorber.
And this right here just shows you the difference so clearly. We're swapping out those big, heavy, spinning machines for things like solar panels and batteries. And yeah, they're clean, they're efficient, but they don't have big moving parts. They have zero physical inertia. So we're basically losing that free stability that we always got as a side effect of the old system. And what we're left with is a new grid that's way easier to knock off balance.
So let's be clear, we've got a problem. A modern grid without that old school inertia is a lot more delicate. But the good news is, there are some absolutely incredible engineering solutions being rolled out to fix it. So let's open up the stability toolbox.
And inside that toolbox, we've got two main heroes stepping into the ring. On one side, you have this mechanical heavyweight, a piece of legacy tech that's found a whole new lease on life. And on the other, you've got this super high-tech, electronics-based solution that's really built for the digital age.
So let's do it. Let's put them head to head. How do these two totally different pieces of tech solve the exact same problem of keeping our grid stable?
First up, we've got the seasoned veteran, the synchronous condenser, or SynCon for short. The simplest way to think about this is like a generator from an old power plant that doesn't actually generate any power. It's just a big, heavy machine that's hooked up to the grid, and its only job is to spin, providing that pure, raw, physical inertia and strength. And in the other corner, you have the modern challenger, the eStatCom. Now, this is a whole different animal. It's a solid-state device, all power electronics. You pair it with a little battery, and it can inject or soak up power in just milliseconds. It's like a super fast, super smart electronic shock absorber for the grid. This table gives us a fantastic side-by-side look. Okay, so SynCons, they're all about brute physical strength. Their real superpower is providing fault current. That's a huge jolt of power you need to trip the safety circuits when something goes wrong. It's like having a really strong electrical backbone, which is absolutely crucial for protecting all the equipment on a weak grid. eStatComs, though, they're all about speed and smarts. They're smaller, way more flexible, and they're perfectly designed for the crazy fast ups and downs you get on a grid that's loaded with wind and solar.
So that's the tech. But what are the folks who actually run the grid, the transmission system operators? What are they doing right now? Where are they putting their money?
And what's happening is pretty fascinating. There's no single answer. You've got places like Great Britain and South Australia. They have a ton of wind power on pretty isolated grids, and they've gone all in on SynCons to give them that bedrock strength. But then you look at Germany, and they're pushing hard for standardized eStatComs. They're betting that the fast, electronic, digital solution is the real path forward.
So who wins the fight? The heavyweight champ or the high-tech challenger? Well, it turns out the answer is both. The future isn't about picking just one winner.
Yeah, the smartest grid operators out there aren't choosing just one tool. They're building a layered defense. They're putting together a whole portfolio of solutions because they know a complex system needs a mix of tools. It's all about putting that physical inertia where the grid needs raw strength, and then using those fast grid-forming electronics where speed and flexibility are what really count.
And this really shows you their thought process. First, you have to diagnose the problem. What's wrong with your section of the grid? Is it that you don't have enough protective strength? Or are you dealing with wild power swings from a new wind farm? Once you know the problem, then you can prescribe the right medicine. SynCons for strength, eStatComs for speed. And the ultimate goal? It's to combine both to build a hybrid grid that's tough enough and smart enough for a zero-carbon world.
And that really brings us to the bottom line. For decades, grid stability was just something we got for free. It was a given. Not anymore. Now it's something we have to actively design, build, and pay for. This isn't just some niche engineering problem anymore. It is quite literally the price of progress. It's the cost of admission to a clean energy future. Which really makes you wonder, right? What other hidden challenges are waiting for us just around the corners we keep pushing forward?